till yesterday we completed looking at certain algorithms which came under the category of informed search algorithm. We saw two basic algorithms. One is greedy best first search algorithm, and second one was A star algorithm. We noted certain issues with A star as well as the greedy best first search algorithm and certain positives. And to avoid the heavy use of space and time with respect to A star algorithm, what we saw yesterday was we would actually have certain additions to this algorithm or certain corrections to this algorithm, the A star algorithm, which may lead to these four optional algorithms, or I should say improved versions of this algorithm. Okay, IDA star, recursive best first search, memory bounded A star, and simplified memory bounded A star. So these are the alternatives to A star, which tries to improve it based on the time and space complexity for certain class of problems. I told you that you can read these algorithms briefly on your own and understand what kind of improvement they have over A star and how exactly they work. Nobody's will be going to ask you a problem to be solved on any of these four algorithms, but you could get in your examination problem related to A star or the best first search or the other uh, uninformed search algorithms that we already seen. Okay, now today we will start the discussion about how exactly people arrive at different heuristics. Okay, and certain properties about heuristics. Can I have multiple admissible heuristics? So we saw concept yesterday of two kinds of heuristics related to A star. One is admissible heuristic and the second one is consistent heuristic. Consistent heuristic is mathematically increasing order, always increasing order heuristic, as and the admissible one also we saw what property it has. Okay, so it has always a better value than the actual cost that you will, sorry, less value than the actual cost you will incur when you follow the step towards goal node using the actual route. So that is admissible heuristics definition for you. Another question in this slide that they try to pose is, can there be only single admissible heuristic for a problem? No, for a problem there might be more than one admissible heuristic. So what they show you in this particular slide is one problem that we already saw, which is called as 8 puzzle problem. So this is the 8 puzzle problem instance for you, where this is the initial state and this is the goal state. Okay, as we can see, we can have multiple heuristics defined, and all of them or some of them may be admissible heuristics. Okay, so there's no proof to this why these heuristics are admissible. The only thing is that these are admissible heuristics as far as 8 puzzles are concerned. This we need to understand. So they have actually used these heuristics for solving multiple problems of A star, and they have arrived at the conclusion that these two heuristics are admissible heuristics for 8 puzzle problem. Okay, now what is the heuristic number 1 and what is the heuristic number 2, that we will see, and we will try and understand how exactly calculation of these heuristics will happen when we actually reach a particular node. Now consider that this is my start state and this is my goal state. My heuristic 1 is number of misplaced tiles. So what do you mean by number of misplaced tiles? That means given a state representation or given a configuration of 3 cross 3 state that we have for 8 puzzle. Say suppose I have some state which I am drawing over here, that has a space here, that has a 1 here, 2 here, maybe 7 here, 6 here, 3 here, and 5 here, and a 4 here, 8 here. Okay, so this is the configuration of some state which may be referred to as say n1. Okay, or I should call it as say m. There's some state m, and for this state, say suppose I want to know what would be the h of m. Okay, basically not h but h1 of n, h1 of m if I want to calculate. So if I want to calculate h1 m, that means I want to apply heuristic 1 to state m. So if I apply heuristic 1 to state M, heuristic 1 says number of misplaced tiles. So I will always compare the state with the goal state and check how many tiles are placed correctly and how many tiles are placed incorrectly. So 6, 7 here are placed in their actual position, whereas I guess no other tile, uh, 5 is misplaced, 4 is misplaced, 8 is misplaced, 3 is in the right spot. Okay, 1 is misplaced, 2 is misplaced, the space is also misplaced. So 1, 2, 3, 4, 5, 6 tiles are misplaced and 3 tiles are correctly placed. So this way H1 of M is 6. 6 tiles are misplaced. So we're just counting the number of misplaced tiles. Now if I see H2, the heuristic 2, they say that this is the total Manhattan distance. Now what is a Manhattan distance? In a grid situation, if I want to calculate a distance between this and this, say suppose this is some grid and I want to calculate distance between this point and this point, that is this cell and this cell, then Manhattan distance is the distance that we can calculate. That's the shortest distance that I can traverse horizontally and vertically, traversing horizontally and vertically to reach this node. So to reach this from this node to this node, if I'm using Manhattan distance, I can only traverse horizontally and vertically. So I may decide to traverse like this, or I may decide to traverse like this as well. Okay, both paths are using the Manhattan based traversal, that is I can go only horizontal and vertical direction. So whichever out of these distances, so there can be such multiple paths available to reach from one cell to the other cell in a grid, but the one which is the least cost is called as the Manhattan distance. The one with the least cost is called as Manhattan distance. So we'll assume that Manhattan distance between two cells, if I want to calculate, say suppose this and this, what we will do is we will go to the this kind of a distance. So I have to travel 1, 2, 3, 4 cells or 4 steps I need to take in order to reach from this node to this node using Manhattan distance. Now there is one other thing called as I'm not sure what it is called as, but in image processing there's one more distance which is called as 8-point neighborhood distance. So for that I can traverse in diagonal direction as well. So the diagonal distance between these nodes is 2, I guess, 1 and 2. Okay, but the Manhattan distance is 1, 2, 3, 4. So Manhattan distance between the actual place and the current place of the node, that will be calculating for every cell or every number time. Okay, for that how we will go about, we'll start with say tile with name 1. It is at this location, its correct position is this location and currently it is positioned here. So I have to traverse Manhattan distance of 1 unit in order to get it right, get it into its correct spot. So that is 1 Manhattan distance away. So 1 is 1 Manhattan distance away from its actual place. Similarly 2, if I see, it is also 1 Manhattan distance away from its correct spot. What about 3? 3 is correctly placed, so the Manhattan distance between its correct placement and its current placement is 0. What about 4? 4 is also 1 Manhattan distance away from its actual position. What about 5? So 5 should be placed here, but currently 5 is placed at this location. So 5 is placed here, and if I count the distance, it will be 1, 2, 3. So it is 3 Manhattan distance away from its correct place. Okay, it was we calculated for 5, 6 and 7, they are correctly placed. So they are 0 Manhattan distance away from their actual place. What about 8? 8 is placed in this corner, upper right corner, whereas it has to be placed lower right corner. So it is 2 Manhattan distance away from its place. So if I calculate sum of these Manhattan distances, it will be 3 plus 3, 6 plus 2, 8. So my H2 of M for the state which I represented above is 8. So this is how I could compute the Manhattan distance for some arbitrary state M. Okay, in this problem, they are telling you what is the Manhattan, what is the heuristic value for the start state. S stands for start state. So H1S. So for this, compared to the goal state, what is, how many are the misplaced cells? How many misplaced cells are there? So I can just count them, and based on that I will get a heuristic value for S1. So I'll just show you what are the heuristic values in here, and I want you to confirm that you understand how they are computed. So I give you a time, okay, to go through this slide, a pen and a pencil if you want, and just figure out that you relate to or you understand how H1S is 8, which is easy. Just you want to check how many tiles are placed correctly out of the number of tiles we have. So how many tiles we have? We have 9 tiles. Out of those 9 tiles, they say that only one is placed correctly. So 8 are misplaced tiles. They are saying 8 are misplaced tiles. Is it like that? Need to just confirm my words. So is 7 placed correctly? No. Is 2 placed correctly? No. Is 4 placed correctly? No. Is 5 placed correctly? No. Is 6 placed correctly? No. Is 8 placed correctly? No. It's 3 placed correctly? No. Is 1 placed correctly? No. So all the 8 numbers are misplaced. What about the space? It is also incorrectly placed, but I'm not counting the space. So the initial description that I gave you, number of misplaced tiles, we are considering only the tiles with numbers. We are not considering the tiles with no number. So we are only considering how many misplaced tiles are which are numbered. So the tiles which are numbered, वो उनका count करेंगे कितने misplaced हैं. Space obviously misplaced है यहाँ पे, तो वो अगर count करता तो ये 9 आता, but it is 8. Okay, so you just need to remember that we are counting the number of misplaced tiles in the sense which are numbered one. Okay, similarly if you count these, the Manhattan distances, you'll count there are 8. 1 2 3 4 5 6 7 8. So they are also 8. So Manhattan distance also we are calculating how many numbered tiles are away from their original place and how much they are away from their original place based on Manhattan distance. So we'll just see few computations. So we'll see for 1, 5 and 6. So to calculate Manhattan distance of 1, oh sorry, but I picked, cursor did not go all the way through. So I'm just showing you calculation for 1, 5 and 7. Okay, so for one has to be placed in this right corner, but it is center top. It is placed at center top, so it has placed over here. So the Manhattan distance between this point and this point, the shortest distance traversing the horizontal and vertical trace would be 1 2 3. Okay, so this is the shortest Manhattan distance. If you travel by this way also, you'll require to travel 3 actions or 3 places. So I should move this to here, then move this to here, then move this to here in order to get it to its right spot. Or actually I have to move this one towards this spot because this is the current state and this is the goal state. If you think in any way, it will be same because the actions here are reversible actions. Okay, so 3 is the Manhattan distance of 1. What about 5? So 5 is placed in center left cell and it should be in right center cell. So it has to traverse 2 Manhattan distance in order to get to its correct spot. So this is 2. And similarly, the calculation for 7 would be, so the 7 is placed here and its actual position is this. So it has to 1, 2 and 3 units. Okay, so that is how it is calculated as 3. So what is the maximum distance? Manhattan distance is between 1 and 7. Maximum Manhattan distance is between 1 and 7, which is 1, 2, 3 and 4. So 4 is the maximum value of any displacement in this case for the 8 puzzle problem. Okay, 4 is the maximum, 3, 2, 1 and 0. So the domain of value of individual Manhattan displacement is 0 to 4. Okay, if the cell is correctly placed originally, it is going to be 0 Manhattan distance away from its origin. Okay, I hope this is understandable. Any issues in understanding this? Also, please understand why they have put this up, why this topic is put up to you is that for any problem, for any AI problem, I may have such different ways of defining different heuristics, but all heuristics may not be useful. Some of them will be definitely useful, some of them might not be useful at all. Now, if I want to actually use any heuristic, I need to understand that what would be its value at the initial state and how this going to get a value when I reach the goal node. Okay, and generally a heuristic value when I reach the goal node would be 0, and it will have some finite value at the beginning, and as we traverse towards goal it should gradually tend to 0. If I'm talking about a cost to reach the goal node, I'm talking about a reverse way, that is a benefit or a profit to reach the goal node, then this particular value initially should be some negative value, and from where I'm trying to reach to 0 or tending to a positive larger value. That you need to keep in mind while you select a heuristic. It should have the property of being admissible, but there can be multiple admissible heuristics, and you need to demonstrate or experimentally understand which heuristic would do better than the other heuristic, because all heuristic may not work or may not be as useful as they look like. Now it is clear that calculating H2n here in this particular case is computationally challenging than calculating H1n, because H1n just need you to test 8 or 9 equality in order to know how many misplaced tiles are. Whereas when I'm calculating sum of Manhattan distances, that thing is going to be, yes, I'm coming to your question. When I'm computing H2n, in that case, it is going to be more time consuming, because for every cell I need to calculate the Manhattan distance for all 8 cells and then do a sum and get a number. Yes, Ankita, do you have any doubt? Want to ask something, or you have asked it in chat window? Go ahead.